the input F, which we call U. So
Anyways,
what are the equilibrium points? For sure, the origin we know is an equilibrium point. So V equals 0 is for sure an equilibrium point. But we see that any V is an equilibrium point, constant. What does this mean? Well, it's obvious. If I have no friction, if I have an initial velocity, I have no force, okay, the mass will keep that velocity. Okay, it will not vary, the velocity will not change over time. Okay, so hopefully this should be quite obvious. Let's continue on this example. Sorry, so this is 1, 2, and 3. So I need to clear this one. Let me copy and prepare. Now let's see the same physical system in which we are also, let's say, interested in the position. So now the equations of motions need to be expressed in terms of also the position. And if we define the position as P, we have m v dot, which is m p double dot equal F. These are really the simplest examples physical that one could think of. But now the state, instead of being only the velocity, includes also the position. So it's P and P dot. This is a special case of the mass spring damper system. Let me, 1 second. Okay, so this is a special case of the mass spring damper system. And we are able now to rewrite the system, the second order system, as two linear first order equations. And we have 0, 1, 0, 0 x plus 0, 1 over m f or u. So with respect to before, now the A matrix is different. So what is the set of initial conditions, sorry, of states such that AXE equal 0? Well, just XE is the set of vectors X such that AXE equals 0, or such that they are parallel to the vector 1, 0. What does this mean? Well, it's, I think, pretty obvious. Now I'm looking also at the position. I have a different situation with respect to before. Okay, V equal constant is not going to be, unless V is equal to 0, is not going to be an equilibrium state. Now, if I look at the position of my mass, now it is changing over time. So for sure, it's not an equilibrium So if we have position and velocity, we are stating that the set of equilibrium states is parallel to 1, 0. So it's something that 1, 0 is this vector. And so the whole subspace is going to be the x-axis. Okay, so this is a subspace of equilibrium points. Physically, what does this mean? Let's look at this particular equilibrium point. Well, it simply states that if I have no force applied to my mass, and I'm in this position here, let's call this P bar, and I have no velocity, the mass will stay in that configuration. So at the same position with 0 velocity, okay? Quite obvious. You could, as an exercise, look at the chemical reaction examples, models, and try to understand these equilibrium points. What do they correspond to, if there's any physical interpretation of these equilibrium points? Okay. So we can now just have a quick look at the slide. So we see if there's something missing in my explanation. The origin is a particular state, etc. So the set of equilibrium points is such that AXE equals 0, the kernel. If A is singular, it means this set of equation will have a non-zero solution. So it means we have infinite equilibrium points. And in order to have infinite equilibrium points, if we see that the determinant can be written like this, it also means that for sure, lambda equals 0 will be an eigenvalue of this dynamic matrix. Okay, so lambda, the presence of an eigenvalue in 0 necessarily gives an infinite set of equilibrium points. And if we think about the concept of modes, remember that for sure we will have, if we have the eigenvalue lambda equals 0, we will have as a mode, natural mode, e to 0t, which is constant. Okay, so there's going to be something related. One component is going probably to stay constant and non-zero necessarily. For example, in the previous system, we had this A matrix clearly has eigenvalue lambda equals 0. Or we can say a little bit more. No, we know that the algebraic multiplicity is going to be 2. This is an upper triangular matrix. So the elements on the diagonal coincide with the eigenvalues. And we also recognize the Jordan form. So we have mg equal to 1. And this has implications in the types of natural modes that we may encounter. Okay, so now for the case of linear systems, we have, I think, some good knowledge. Let's just look at some examples in a 2D setting so that we can use and focalize better these concepts on the phase plane. So let's take this example, A equals 0, 1, 1, 0. Clearly, this matrix is non-singular, so it will not have lambda equals 0 as an eigenvalue. If we compute the eigenvalues, so the determinant of lambda I minus A, we will have lambda squared minus 1. And so the two solutions are going to be lambda equal minus 1 and lambda equal plus 1. Okay, so what we have seen in some previous lecture is we have two distinct eigenvalues. Each of these eigenvalues is going to be characterized by an eigenvector u1 and u2. And so each of these eigenvectors is going to generate a subspace. And these subspaces are going to be for lambda equal minus 1, this straight line here, okay, so on. Don't want to ruin this nice plot. And for lambda equal plus 1, this other straight line on the, let's say, main diagonal. So we have these two subspaces. We already understood when we were studying the state, free state evolution or zero input response in the state, that if we were starting on that, on each of these eigenspaces, we were staying there, and with the time evolution that was determined by the eigenvalue. So if we think about this phase plot and we search for equilibrium points, we see that there are no, by looking at the vector field, we see that there are no equilibrium points except the origin. You see there are no, we have vectors here everywhere. So this is telling us that in this location, the derivative is non-zero and has that direction. Of course, since the matrix A is non-singular, we have a unique solution to AXE equals 0, which is the origin. Okay? So unique solution. And this plot is going to be also useful in a little while to interpret the concept of stability. For now, we are just concentrating on equilibrium states. Let's see another case in which the determinant is equal to 0. So we have now understood that determinant equal to 0 means the presence of, for sure, at least one eigenvalue in 0, which means infinite equilibrium points. And again, we are in a situation in which we have two distinct eigenvalues, so we can find two distinct eigenspaces. Let's see what happens. This eigenspace here is the one corresponding to the eigenvalue lambda equals 0. And we see that if we start on any point on this eigenspace, we stay there. And this is another way of saying that all these points along this line are equilibrium points. And this can be easily determined by solving AXE equals 0. We find that all the equilibrium points are going to be parallel to 1, 1, which is exactly the eigenvector corresponding to lambda 2. So I would like to point out that you see there's nothing really complicated, okay? We're just making little steps. Now we are still, let's say, in the beginning, but there's one aspect that maybe now is getting more clear. we are making a lot of connections between the concepts. Okay, we talked about natural modes, we talked about eigenvalues, now we're talking about equilibrium points. So all these can be connected somehow, and this sometimes is a difficulty of this course, is to make these connections. It's not only a question of learning every single step, but is understanding and making these connections, let's say, personal. Okay, so now that we have defined the concept of equilibrium state and we saw how these equilibrium states can be characterized in the linear case, we're going to talk about the concept of stability. So we will start again through some simple consideration, and then we will see what happens, how we can characterize stability in the linear case, and later on we will extend all these, some of these concepts to the nonlinear case. So first, let me try to highlight a simple system, okay? Imagine we have our mass spring damper system. And we assume we have no inputs. And this is, let's say, the equilibrium configuration. So now we can be a little bit more explicit. Remember that we have chosen the easiest state vector, which was something like delta and delta dot, where delta is a deviation with respect to the position at rest. Okay, so this mass at rest will be, rest means no velocity and the position remains constant, okay? So this concept of rest is exactly what we have now defined as equilibrium point. So we found that the dynamic matrix was 0, 1 minus k over m minus mu over m. Clearly, the determinant of this matrix is different from 0. So AXE equals 0 has a unique solution. This is a square system, which is the origin. And the origin here means the position is at rest and the velocity is 0. Okay, so now let's make an experiment. And let's start from an initial condition, which is different from the equilibrium state. Because if we start from the equilibrium state and we have no inputs, we know by definition that we will stay there. How this mass will move? Well, we have seen that how this mass will move depends on the eigenvalues of the system. And for this specific example, we studied the different types of eigenvalues. In particular, this mass is going like this or like this. So with a low damping or high damping is going in any case to converge back to the original rest position. So this is what we may call, in simple words, stability. But in fact, this is a little bit more than stability, because not only the state, position, and velocity does not diverge, we do not see the mass going away from this rest position, but the mass, position, and velocity is going back to the original rest position. So this experiment is an example of asymptotic stability. Okay, so we still have no example of, we have added here a term which is asymptotic stability. Asymptotic, yes. So can we find an experiment in which the mass does not go back to the rest position, to the equilibrium point? Well, if we assume that both elasticity K and mu are different from zero, clearly, from any initial state different from the origin, I will go back sooner or later. Slower, faster, with oscillations, without oscillations. So I will always have this asymptotic behavior. But if I put K equal to zero, I clearly see that now A becomes 0, 1, 0 minus mu over m. Now the determinant of A is equal to 0. We have infinite equilibrium points. And physically, this is something like if I move my mass from the initial position and start with 0 initial velocity, I will stay there. Okay, I have no spring in this specific situation. Or, so I stay still. I'm not going back to the original state. Okay, so this is an example of just stability or stable behavior, not asymptotically stable behavior. Okay, let me insist on this. Let's do another experiment. So number 1, number 2, and number 3. Now, let's assume that K is different from 0, but mu is equal to 0. So this corresponds to a mass connected to some fixed point and with no friction, no viscous damping, okay? So we clearly understand that the motion from any initial condition, well, we already know what the motion is, because from any initial condition, the zero input response is going to be characterized by the natural modes. And when we studied the natural modes for this system, the case mu equal to 0 gave us two eigenvalues, lambda 1 and lambda 2, which were purely imaginary, something like k over m, j k over m. And we know that in this case, we have a purely periodic motion. Okay, so we do this experiment. We take our mass from our rest position, 0 delta and 0 velocity, and we start from a different initial position, again, for example, with the 0 velocity, but not necessarily. What happens is that the mass is going to oscillate and will not stop. It will not go back to the equilibrium point. Okay, so is this stable? Well, yes, this is still stable, but not asymptotically stable. Okay, because in time we have no, pure oscillation in the position and also in the velocity. So it's not diverging, it's not converging to 0. If we think that this is a delta of t. So what we have here is, what we have done here is we are connecting the concept of stability to what happens if I have a non-zero initial condition. In particular, if I have a non-zero initial condition, if my state goes back to the equilibrium point, then I will have asymptotic stability. If the state remains, let's say, bounded, you see that it does not go over some given values, then we are going to say that it is stable. All the other cases in which the state will diverge in time, it's going to be unstable. But now we are characterizing this concept through the zero state evolution, which we are able to fully understand now with all the ideas we've seen previously. Okay, so for now, for linear systems, we are going to say that a system is asymptotically stable when the zero input response tends to 0 for any initial condition. So be careful, this any initial condition is important. It's not just for some initial conditions. Okay. A system is stable or marginally stable if it remains, the zero input response remains bounded. It does not diverge and is unstable if the state diverges for some initial conditions. Okay, so be careful in the use. Okay, let's go back to our 2 previous cases. So we see that in this situation, we have that there are some initial conditions, and here most of the initial conditions for which the state diverges. Even if I have some special initial conditions for which the state goes directly to the origin, so goes back to the equilibrium point. So it's not converging to 0 for any initial condition, but there are some initial conditions for which the state is diverging, so this system is clearly unstable. Let's see the other example. Is the state converging for every initial condition to the equilibrium point? Well, is it converging to the origin? No. Clearly, if I start from this initial condition, I will end up asymptotically to this state here. But I will not go to the origin, okay? So this is not asymptotically stable, but it's not diverging, so it is just marginally or just stable. Okay, so we have these simple definitions, which for now are definitions of a system. We say that the system is asymptotically stable. The system is stable or unstable. And this is, again, a specificity of linear systems. It's something that we can state only for linear systems. In a few minutes, we're going to understand that for nonlinear systems, this is not going to be true anymore. Okay, so from now on, things are going to be, it's just an application of what we did before. We would like to be able to understand when a linear system is asymptotically stable or not. From the previous examples, it is quite clear that the characterization of the zero input response through the natural modes is helping us in understanding when a system is asymptotically stable or not. Because the only time functions which appear in the zero input response are the natural modes. And since we should look what happens for some generic initial condition, okay, we are going to have clearly if all the eigenvalues, you see in this slide, which is just an old slide that we saw previously when we were summarizing all the natural modes, ATX con 0 is going to tend to 0 for any initial condition when all the natural modes will decay to 0. All of them, because we are asking that for any initial condition, the zero input response should tend to 0. And we saw that all the natural modes, the divergence, convergence of any natural modes will depend on the real part of the eigenvalue, of the corresponding eigenvalue. So we can directly state that we're going to have asymptotic stability for linear system if all the eigenvalues are such that their real part are less than 0. Okay? If the eigenvalue is real, e to the lambda real part is negative. Did I say something different? I don't know. If we have aperiodic modes, so corresponding to real eigenvalues, negative eigenvalue corresponds to negative real part of the eigenvalue, so this is converging. If we have pseudo-periodic mode, here is the real part of the eigenvalue, so this exponential, if alpha is negative, will tend to 0. Even if the matrix is not diagonalizable, the exponential will always win on any other time function present in our natural modes. So we can now fully characterize stability in terms of the eigenvalues. And we have, let's say, 3 possible situations. The easiest one, the one that we will always try to obtain, how it's not clear yet, is asymptotic stability. And so we can state now that a linear system is asymptotically stable if and only if all the eigenvalues have strictly negative real part. Okay, so that's obvious. We can state by recalling all the different natural modes that, okay, we may have some behaviors, some natural modes, which will not converge to 0. When is this happening, but are not diverging? Well, we saw when we have a natural mode like this, or when we have a natural mode like this. it's not sufficient to say, okay, if all the eigenvalues are such that the real part is less or equal to 0, then we will have stability, marginal stability. Because we know that there are situations in which the real part is equal to 0 when the geometric multiplicity is different from the algebraic one, in which, yes, we have this natural mode, but we have also this natural mode, and this is clearly diverging. So the difference here lies on the geometric multiplicity. So if the geometric multiplicity is equal to the algebraic multiplicity, we are in this case. Otherwise, we have some, for the case real part equal to 0, we have diverging behaviors. And this sums up in saying that linear system is going to be marginally stable if and only if all the eigenvalues have real part less or equal to 0, and those who have real part equal to 0 are such that their algebraic multiplicity coincides with the geometric one. Okay? So you see, again, now that if you didn't study in time, you are having maybe difficulties in remembering what's a geometric multiplicity, how is it connected to the algebraic, how is it connected to the natural modes. So that's why I'm always insisting in try to follow and keep the pace with the lectures. And okay, so the last case is when a linear system is unstable. Clearly, if we have at least one eigenvalue which has positive real part, then we will have a diverging natural mode. But this is not necessary. We may be in this situation here. So system is divergent, unstable, if also in the case where we have 0 eigenvalues with geometric multiplicity different from the algebraic one. Okay? So stability now is going to be characterized for linear system through the real part of the eigenvalues and through the, in some cases, the geometric multiplicity when we have multiple eigenvalues. Now, this concept... Sì.
Posso farle una domanda?
Certo, sono qui apposta.
Io non ho capito solo la differenza che c'è nel caso di marginalmente stabile, quando ho il Jordan block e la parte reale di lambda I è uguale a 0, mi è chiaro che diverge, però non dovrebbe essere instabile quel caso? Ripeto la domanda magari.
Allora, so the question is, can I clarify the concept of stability in the case of the presence of a Jordan block? Is that similar to what you're asking?
Sì, nel caso marginalmente stabile.
So let's assume we have just one eigenvalue equal to 0. Repeat it. Let's take the case n equals 3. Okay. So we have roughly, I think, 3 situations. So the first one is the dynamic metric is identically 0. Second case, we have 0, 1, 0, 0, 0, 0, 0, 0, 0. Third case is 0, 1, 0, 0, 0, 1, 0, 0, 0. So all these cases have a characteristic polynomial lambda cube. So the algebraic multiplicity is equal to 3. But clearly, this has mg equal to 3, mg equal to 2, and mg equal to 1. Why do I say clearly? Well, because this is a diagonal case, and we see that the matrix is diagonalizable if and only if the geometric and algebraic multiplicity coincide, or if you prefer, mg is the number of Jordan blocks. So we have 3 Jordan blocks here. In the second case, we have 2 Jordan blocks. And in the third case, we have 1 Jordan block. Okay? So natural modes. Here we have only the natural mode e to the 0t. Here we have e0t and t e0t. Here we have e0t, t e0t, t square over 2 factorial e0t. Or if you prefer, 1 t square over 2. Okay, so this is marginally stable. This is unstable due to this natural mode, and this is unstable due to both. Is it more clear now?
Chiaro, sì.
Okay. Any other questions? Ok.
Che pensa ste cose su Conte, non ne so.
Per favore. Microfono. Okay, let me add another important piece of information. A very common error is looking at a time evolution and seeing that the time evolution diverges over time for a given system. And so this divergence sometimes is confused with the concept of unstable system. In particular, let's take a simple system, minus 2x plus u. Okay, so n is equal to 1. We have only one eigenvalue equal to minus 2. We know that this system is asymptotically stable. For now, this is extremely well known. But if we do the experiment, so this is my system here, we choose as output just the state. If I apply a step input here, the output, the corresponding output, is going to be something that will go to a constant value. Okay. But now if I choose another input, let's imagine t, delta minus 1t, okay, the corresponding output y of t, but this coincides with the state x of t, is going to be something that will diverge and will go along a straight line. So we here see a divergence. That's awful. Okay, we see something diverging. But this clearly does not mean that the system is unstable. Why? Because we have defined the concept of stability for a system with no inputs. It's just we are looking at perturbations of the initial conditions when no input is applied. So we are looking at the zero input response. U is equal to 0. So this diverging, apparently diverging behavior is totally natural. Okay, if I'm pushing, if I'm, for example, applying a force which is constantly increasing to my mass spring damper system, the position will change over time, will diverge from its original equilibrium point. Okay, so be careful. Finding a full response which is diverging because of the presence of the input, this does not, of course, mean that the system is unstable. Okay, stability is a free state evolution concept. It is independent from the input, at least at this stage. Okay, so that's roughly what we have here. And then we already discussed these cases here. Let's also discuss the difference between state and output. Okay, we are talking about stability, so we are in the case where we look at the zero input response. Okay, if we have that x of t, zero input response, is converging to 0 for any initial condition, okay, so this means that our system is asymptotically stable. Can we say the same for the output? Can we say that if we observe the measured variables or variable one output, and we see that for any initial condition of my system, it goes to 0, is this implying that the system S is asymptotically stable? The answer is no. Why? Again, I've made now this almost a stupid example several times, but it makes things quite clear. Imagine I'm driving my car. No, let's change a little bit. Let's imagine we have our mass spring damper system, and we have some engine that is driving my mass. Okay, so if for some reason the engine is breaking and is burning, the temperature, which now could be also considered as a state variable because it will satisfy some differential equations, etc., will clearly diverge because the system is burning. So the potentially the temperature will grow to higher and higher values. So if I'm just measuring the position of my mass, probably until the motor does not really break or something different happens, I will not see that internally the temperature is increasing. So the output may not let you see everything that is happening in the state. So let's see this through an example. Let's compute explicitly the zero output response. Okay, so the difference is we have the state zero input response and just pre-multiplied by the C vector. So it's a linear combination of the motions of the zero input state response. When we, for example, use the known formula, the spectral decomposition for the exponential, okay, we have e to the at, the sum, if we have n different, for example, natural modes, e lambda I, ui, vi transpose. Now, I pre-multiply by C, C can be brought inside the sum. Then I have e to the lambda it, which is a scalar. So finally, I can move and obtain this. So you immediately see that if this C times ui quantity is equal to 0, the corresponding natural mode will not appear in the output zero input response. Okay, this is hopefully quite clear from this analytical expression. So if CUI is equal to 0, the corresponding natural mode E lambda IT is not present in the output zero input response. So if this is, for example, an eigenvalue real and positive, so the natural mode is clearly diverging, in the state evolution zero input response, I see clearly this divergence, but in the output zero input response, I do not see, if I have this situation here, that divergence. So if all the other natural modes are converging, I could be tempted in saying that the system is asymptotically stable, while it is not. Okay, there's an example here, a suggested example. Compute this output zero input response and giving values to lambda 1 and lambda 2, or understanding the cases in which they are positive or negative, if you can find such an example that corresponds to this situation. Okay, so we can summarize this. There are some other examples. We can summarize this by saying, okay, sorry, it's here. If the system is asymptotically stable, all the natural modes will be converging. The output, zero input response, will be converging. If the system is marginally stable, then similarly, the output zero input response will be bounded, while the converse is not true. Okay, and this is exactly what in both cases we just saw. Okay. Now we are able now to characterize stability of a linear time invariant system just by looking at the sign of the eigenvalues lambda I. Well, we know that the eigenvalues, given a dynamic matrix A, these eigenvalues are the solution of the characteristic polynomial. So apparently, a possible algorithm could be, given a dynamic matrix, find the eigenvalues. Once we have the eigenvalues, then see the real part of these eigenvalues. If all have a negative real part, the system is asymptotically stable. Otherwise, we may have just stability or instability. Well, in fact, here we are only really interested in the sign. And there's this almost amazing result, which I will just highlight with an example. Okay, so here we have, okay, each of you now is going to give me a number. Okay, let's make this almost magic test. Wait 1 second. Okay, let's start like lambda cube. Okay, number 14, 10. Okay, positive, negative, real, whatever, complicated, whatever, a number 3. No fantasy. 37. Last one. Oops. Minus 45. Okay, so now since I'm extremely fast in computation, I can tell you that the 5 solutions here do not have all real part less than 0. So this is not because I'm able to compute the solutions. This is a 5th order polynomial, so sometimes we do not even have the closed form solution, etc. This is because there's this very nice result, and there's even a necessary condition which help us just in understanding if all the solutions of a polynomial have the same real sign, okay? Sign of the real part. And here what I've used is a necessary condition. So a necessary condition in order for all solutions of a given polynomial to be such that they have real part negative is that the coefficients have all the same sign. Now, I was quite lucky that at least one of you chose a negative sign, because otherwise I couldn't say anything. Now, so here, thanks to this negative or this negative -1 coefficient, I knew that not all solutions were negative, real part negative. Okay, just one remark. So this is a really very simple and very useful result. Okay, because without computing all the solutions of the possible complicated polynomial, we are at least able to say if it is worth going on or not to check stability or not. A 0 coefficient is different sign, okay? So if we had lambda 5 plus pi lambda cube plus the square root of 3 pi, what, I don't know, cube lambda square plus lambda plus 2, okay? Without doing any computation, I can already say, since lambda 4 has 0 coefficient, that this polynomial does not have all its solutions with a negative real part. Okay, so we have this first result, necessary result, but we like necessary and sufficient results. We would like to be able to determine if and only if all the solutions of a polynomial, without computing them, have negative real part or not. And this is possible through this route criteria. Okay, so we start by considering a generic polynomial. For us, this is going to be the characteristic polynomial. And we saw the necessary condition. Now we're going to build a table. And since this criteria is called route criteria, this table is going to be called the route table. Now, there is no, in this course, there's no proof of this result. It's really very, let's say, mechanical. We're going to build this table, and then there's a criteria that says if all the coefficients have the same sign, then all the roots of the polynomial will have negative real part. Okay, so no proof, no insight, no intuition. It's really something that comes from nowhere. Somebody found this result, and this result is really very useful, at least for you, for exercises, etc. So let's build this, let's start building this table. So first, if the polynomial is a polynomial of order n, this table will have n plus 1 rows, okay, from 0 to n, or from n to 0. And the first two rows, so row n and row n minus 1, are simply built by looking at the polynomial and taking the coefficients from the highest order to the lowest one and alternating these coefficients on row n and row n minus 1, which means the first coefficient is an, the second coefficient is an minus 1. Then we have an minus 2, an minus 3, etc., etc. Okay? So the first two rows are built just by inspection. We look at the polynomial and we can directly write the first two rows. Then we need to complete all the other rows. And there's a recursive, let's say, formula, almost recursive, which goes like this. Let's take this B1. Okay, B1 is equal to minus 1 over the first element of the previous row times the minor that has the first two elements of the two previous rows and the next two elements of the two previous rows. You see, it's going to be much easier than saying it. So this is B1, okay? Let's see B2. Let's see once we understand the mechanism, it's going to be easy. B2 is again minus 1 divided by the first element of the previous column, row. And then the minor, as you see, the same first column, which are the first two elements of the two previous rows. And the second column is the next two elements. You see, an minus 4, an minus 5, and so on. If we have here B3, it's going to be minus 1 over an minus 1 times the minor an minus 1, and then an minus 6, an minus 7. So this is the mechanism. And this is going to be repeated for all the other rows. For example, let me clean this so that I can draw here. Let's see C1. The algorithm says minus 1 over the first element of the previous row. So previous row starts with B1, so minus 1 over B1. Okay. Then the minor, which has as first column, the first two elements in the two previous rows. So an minus 1 and B1. Okay. And then these two here, an minus 3 and B2. If I look for C2, it's going to be again minus 1 over B1, minor an minus 1 B1, and then these two elements here. So here I have B3. Okay, so the mechanism now should be clear in how you compute. So you see, it's all simple computation. So let's now a little bit comment on how to complete this table. First, well, the first two rows here will have a finite number of elements, because this finite number of elements is exactly the number of coefficients of my polynomial. So here, at a certain point, I will stop. And depending if I have an odd or even number of coefficients, I may have two elements here, or I may have one element and 0. So if I do not have, I may have only one element. If I have an empty space, which may be necessary in the further computation, I will put 0. We will go through some examples, etc. And the more we go down in this table, the less elements we are going to have. Okay. And every time we have some places which we need for this computation, which are empty, we will put 0. Maybe it's not 100% clear, but through an example, this is going to be extremely simple. Then, since we are doing this minor, this multiplication, etc., the final result is unchanged. So it means that we can build an equivalent table, Roth table, if we multiply an entire row by a positive number. And this can be very useful in order to simplify these computations. Okay, now that we have this algorithm, we first establish the results, and then we go through one big example. That should be more than enough. So we have a necessary and sufficient condition. Before stating this necessary and sufficient condition, when we look at the table here, we could say, but what happens if one of these elements is 0? These cannot be 0, because otherwise I do not start building my route table, because the necessary condition is telling me that, an cannot be 0. An minus 1 cannot be 0, because otherwise the necessary condition is not verified. So maybe B1 could become 0. If these two columns are linearly dependent, I will have B1 equal to 0. So this is a case which then leads to a problem, because when I write 1 over B1, this cannot be computed. But this is a case that we define the table cannot be completed. And if the table cannot be completed, then for sure, not all the roots have negative real part. Okay? So from now on, we're going to work only or establish this result in the case when the table can be completed. And the result, quite amazing, says that all the roots will have negative real part if and only if all the elements on the first column of the route table have the same sign, or if there is no sign change. Okay? No explanation. You need to take this as it is. So if we apply this to stability, of course, if this polynomial is a characteristic polynomial, then we have stability if and only if there are no sign changes in the first column of the route table. Another sometimes useful result is that the number of sign changes, so if I have sign changes, I know for sure that the system is not asymptotically stable, but the number of sign changes gives also the number of roots with positive real part. This may be useful in some contexts. Okay, let's go through an example. I have a fifth order polynomial, and let's start building our route table. Okay, I have coefficient 1, coefficient 1, coefficient 2, coefficient 1, etc., etc. Okay, so the first two rows are evident. Questions? If there's one step in this, let's say, pseudo algorithm which is not clear, this is the right time to ask. Okay, no questions? Then we can start by computing the next row. So I take the first element here, I must take -1 over the first element of the previous row, and then the minor 1, 1, 2, 1. Okay, so this is exactly what is written here. And so this is 1 minus 2, so it's -1. And here we have the change of sign, so this gives 2. Sorry. Minus is 1, okay, because it's 1 minus 2 minus 1, change sign, plus 1. Okay, and this is a number here. And again, this is going to be -1 over the first element of the previous row, and then the minor, which has this first column and this as second column, and so on. Okay, so try for a few minutes, try to complete without looking at the solution. Just try to check if you got the algorithm correctly. I will just recall these formulas. Okay, just try for a few minutes. At least one pair of numbers. The polynomial, sorry, the polynomial, where is the polynomial? Polynomial is 1, 1, 2, 1, 3, 1. So number 5. something like this. 1, 1, 2, 1, 3, 1. 1, 1, 2, 1, 3, 1. Okay, so this is a polynomial. So try to build the right table. And then you can check. Because by trying, you see if there's something not clear in the way you understood the algorithm. Okay, so this is the algorithm, and you have all the tools to try yourself. And so you have also the way to say if the system characterized by this characteristic polynomial is asymptotically stable or not, by applying directly the criteria. Try to compute B2 and try to compute, for example, C1, so that you can check if it's okay. Verrà zero. Okay. I guess this is hopefully clear enough. So your colleague was asking when I'm going to compute this element here, the minor would be 1, 1, and then 0, 0. And this 0, 0 will give 0 here. Okay, and that's why this table is always becoming, let's say, shorter and shorter as number of elements in the columns. So once we have completed, you have completed this. I don't think there's any multiplication by a positive number to simplify the computation here. I don't recall anything. We can just say that this is positive, 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 negative. So we already know that not all the eigenvalues or solutions have negative real part. If we are interested in knowing how many are positive, we see that this is negative, positive, and positive. We have two changes, two sign changes. So among all five eigenvalues, I know not all will be with negative real part, but I can say that I have two that have positive real part. So this opens the way to checking really stability for even large order systems. And now, okay, as a special case, this is really a very, very common special case, so it is worth mentioning it. Suppose we have a second order system the characteristic polynomial is a second order polynomial. If we build the route table, you see we have first element, second element, third element, and we stop. Here we put 0. And this last element here is minus 1 over b times a, b, c, 0, which is equal minus 1 over b minus cb. What is this a here? Sorry, this is a clear typo. Strange that I never noticed. And so we have C here. Okay, so this is a very special case. Why? Because the necessary and sufficient condition is saying this second order polynomial, we have both eigenvalues with negative real part if and only if A, B, and C will have the same sign. But this is also the necessary condition. So in this special case, and of course n equal 1, it's not even the case of mentioning it, but for n equal 2, the necessary condition is also sufficient. This is going to be used very, very often in exercises. Okay, let's have a 5 minutes break.
Professore, posso chiederle una cosa?
Sì.
Nella slide precedente...
Ricordi poi dopo di spegnere il microfono, però.
Sì, sì. Nella slide precedente, quando stava facendo i calcoli, esatto, lo 0 nella quarta riga.
Questo?
Sì,
sì.
Non capisco perché il minore ha la prima colonna 1, 0.
Perché ho sbagliato. Grazie.
Ok. Perfetto, grazie.
Sorry, there's another typo here. This is not 1, 0 because it's the minor 1, 1 and 0, 0. Okay, so this is 1. Okay, so 2 typos here. Good. As a general comment, if you find any typo, please write an email so I can correct it. Okay. Okay, so start this last part of the lecture. If possible, I will spend this last part first with just maybe one small exercise and another consideration, and then I will move to nonlinear systems. So let's consider this system. So x dot equal 0, 1, 0, 0, 0, 1, 2, minus 1, minus 1. X plus 0, 0, 2. Okay, we do not even consider the output for now. So the first question is stability. Study stability of this system. And so we need to compute the characteristic polynomial. So the determinant of lambda I minus A, or A minus lambda I. So the determinant of lambda minus 1, 0, 0 lambda minus 1, minus 2, 1 lambda plus 1. Okay, so with a little bit of computation, we should find something that looks like lambda cube plus lambda square plus lambda minus 2. How did I get this? Because this matrix has a special structure that we're going to see when we will talk about state feedback, etc., etc. But please check, okay? We can just briefly check in MATLAB just because it allows me to show you a little bit also how to use MATLAB. So let me share this screen. Okay, so this is a typical MATLAB interface. We are, hello? Okay. We have as a matrix 0, 1, 0. Second row is 0, 0, 1. Third row is 2, minus 1, minus 1. We check, yes, it's okay. So we compute the eigenvalues of this matrix, and we see that we have a positive eigenvalue. This is 0 imaginary part, so it's a real and positive. Then I could also use the command roots finds the roots of a polynomial, and you just need to put the coefficients of the polynomial in a vector. So roots, I have a parenthesis, and then the vector is the polynomial I think is correct. So 1, 1, 1, and minus 2. And if the roots coincide, they do not coincide. Sorry. And the roots, the roots coincide. Yes, just in different order. Okay, so this is a, let's say, a cross check to verify that what I've written is a correct polynomial. So let's go back to the slide. Okay, so the necessary condition is not satisfied. Okay, so for sure, not all roots or eigenvalues have negative real part. So the system S is not asymptotically stable. So the next step is, let's use a special feedback. I need an extra page. So this is it. So let's choose a specific input, which has the following form. 0, 0, k, x. So what is this? Remember, u is a scalar because we are looking at one input case, okay? This is a system with one input. This was clear from the dimension of the B vector. X is a three-dimensional state vector. And this is a linear combination of the state, okay? It can be written as U equal F row vector times X. So this is usually called a state feedback. Why feedback? Because I'm bringing back at the input something that comes from the state. So I could represent this as I have F, so I measure somehow the whole state, X, I multiply by the row vector F, I have my input, okay, and this goes into my system. So you see that I obtain a new system, which is different from just S, okay? It's a closed loop system in which I have used a state feedback. I could also write U equal Fx plus a new input V, which corresponds in having this. I'm closing this feedback, but I'm have an extra, let's say, possibility influencing my system through input V. So this is a different system from S. The question is, could we find an F such that the new system is asymptotically stable? Okay, let's elaborate on this. And let's look at this new system. Since we are talking about stability, I'm going to put V equal to 0. No input to this new system, okay? So V equal to 0. And let's compute this new system, the closed loop system. I had X dot equal AX plus BU. Now I'm using U equal Fx. Okay, what is the effect of this loop? So this is a state feedback. Okay, I will replace this specific choice of my input, which depends on the state, in the original expression of my system. I obtain x dot equal ax plus bfx, which is written as a plus bf times the state x. So we had an original system S with a dynamic matrix A, and now through the state feedback, I have a feedback system which has a different dynamic matrix, A plus BF. And so hopefully, by choosing properly F, I may be able to make A plus BF asymptotically stable. So the new closed loop system asymptotically stable, or all the eigenvalues of A plus BF with real part strictly less than 0. Okay, let's compute in our example A plus BF. 0, 1, 0, 0, 0, 1, 1, 2 minus 1, minus 1. Then I have 0, 0, 2. F 0, 0, okay. Okay, so this becomes 0 plus 0 times 0, so 1 plus 0 times 0, and so on. So these are, the first two rows are evident. The third row is 2 plus 2 times 0, okay, it's still 2, minus 1, 2k. Okay, so this new matrix will have a polynomial which is going to be lambda cube plus 2k lambda square plus, sorry. Let me write it below. So this new Cartesian polynomial will be lambda cube minus 2k. Mi dica.
Professore, mi scusi, l'ultimo elemento in basso a destra della matrice non dovrebbe essere 2K?
Ah, c'è un meno 1, aspetti, meno 1 più 2k. Questo diceva?
Sì.
Ok, grazie.
Di nulla.
Sorry. Okay, so this becomes plus 1 minus 2k lambda square plus lambda minus 2. And we see that this specific choice of my feedback, there are no values of k such that this polynomial is okay, in the sense that it has all its roots with negative real part. Okay, let's make another different choice. So this was with f equal 0, 0k. Maybe if you understand how I'm computing these polynomials, you see that we need to change, let's say, to add something that will change this sign. So let's try with a different f prime. Let's leave everything parametric and let's see what happens. K1, K2, K3, these are scalars. Again, when I compute A plus BF, I will obtain 0, 1, 0, 0, 0, 1. Then I will have plus 2K1, so 2 plus 2K1 minus 1 plus 2K2, and where is it? Minus 1 plus 2K3. Please check, okay? Again, computing the characteristic polynomial of this.
Questa sarebbe A più BF primo,
BF primo, ok, BF primo. That's good. I will obtain lambda cube plus 1 plus 2 mobs minus 2K3 lambda square plus 1 minus 2K2 lambda minus 2, 1 plus K1. Okay, so now we can first we could compute the route table. 1 minus 2K3, 1 minus 2K2, and minus 2, 1 plus K1. Okay, the necessary condition require that since the first coefficient is positive, we should have 1 minus 2K3 positive, 1 minus 2K2 positive, and 1 minus K1 negative. Okay, so when I compute this element here, we'll have minus 1 over 1 minus 2K3, the minor, rather complicated. So I will have something that will depend on the products K2, K3, which is something I would try to avoid. So let's make for now a simplifying hypothesis. Let's see if it is sufficient to put K2 and K3 equal to 0. So this means that F prime is just K1, 0, 0. So with this hypothesis, the polynomial becomes, it's simpler, of course, plus lambda square plus lambda minus 2, 1 plus K1. And we still are looking for K1 such that the characteristic polynomial has all its roots negative. Okay, so again, the necessary condition requires that 1 plus K1 should be positive, negative, which is K1 smaller than minus 1. But this is just a necessary condition. Okay, so the route table simplifies in, what is this? Hello? Okay. The route table simplifies in, let me rewrite it. 1, 1, 1 minus 2, 1 plus k1. And so this element here is minus 1, 1, 1 minus 2, k1 plus 1. And this is equal to 2 k1 plus 1 minus 1. Sorry, plus 1. Okay. So this is 2. Please check. Now I'm going a little bit faster because I didn't think it would take so long. So if everything is correct, here we have 2k1 plus 3. Here I have 0, and here I would have minus 2, 1 plus k1. And this completes the table. So the necessary and sufficient condition requires, since this is positive, it requires that also the other two elements should be positive. This is positive due to this condition here, so we just need to check if this is compatible with 2k1 plus 3 positive, which means k1 greater than minus 3 half. So yes, it looks like we have an interval. If k1 belongs to minus 1.5 minus 1, then the new system, the closed loop system, is asymptotically stable. Okay, so we just saw an example in which a particular state feedback was able to create a new system, the closed loop system, with different stability properties. And this is going to be one of the main tools or objectives, not necessarily this is going to be the technique we're going to use, but when we start from an unstable system, which is something we would like to avoid as much as possible, for sure, we will need to stabilize it. And this sometimes is going to be achieved through a state feedback or through some other techniques. Okay, let me now just spend a few words on nonlinear systems. I refer to the slides of Professor Oriolo. In the slides, I think I wrote, yes, the topics that you should look in those slides. So it's not all the slides. In any case, hopefully by Sunday, I will import what I think is strictly necessary in our version of the slides. Okay, first concept, equilibrium point. Okay, we define XE such that for a nonlinear system, x dot equal fx u, the equilibrium system is equilibrium state is such that 0 equal fxa 0. 0 input. I start from the state xe, I remain there. Well, this is a specific choice. There are some other situations, which I will comment in a while, in which we may have a non-zero input. But for now, let's consider just 0 input. One difference with respect to linear systems is that we may have a finite greater than 1 number of equilibrium points. So they are not necessarily one or infinite. We may have, for example, 2 equilibrium points. So that's a big difference with respect to linear systems. And then, since we may, for example, have 2 equilibrium points, the concept of stability now needs to be a little bit more precise. So what did we want to do? We wanted to check if I have a small perturbation with respect to my equilibrium point, and I would like to check if the corresponding state evolution at least remains within a neighborhood of my equilibrium point, does not diverge. Okay, so this is, we can write this even graphically by saying, let's choose any epsilon, as small as we want, okay? And let's start with an equilibrium point xe. So this epsilon defines a neighborhood. This is a circle. Let me just, sorry, try one thing. I know that, okay. Okay, so that's much better. And so I'm defining, let's make it a little bit bigger. Okay, so this is a circle around, we are just reasoning in the plane for now. And this circle has radius epsilon. So the question is, can I guarantee by constraining my initial conditions that the state evolution from those initial conditions will remain within this ball or circle or disk of radius epsilon? So the question is, if there exists a delta which may depend on epsilon, positive, such that if I start inside the circle of radius delta, x of t will remain inside the circle of radius epsilon. Let me highlight this. I always need more. Let me highlight this graphically. So, given epsilon, I'm looking for sorry. Okay, I'm looking for another, practically another circle, such that if I start inside for any initial, sì.
Io vedo lo schermo bloccato, non so se è un problema solo mio o anche degli altri.
Il mouse non lo vede? No, scusi, no. Che mouse? Non c'è mouse.
Sono rimasto bloccato all'X punto. Però che lei sta scrivendo, quindi non so...
A me funziona correttamente, per esempio.
Va bene. Oh, funziona.
Provo
Quindi...
a rientrare.
Sì. Si vede, mi confermano dalla regia che si vede. Ok. quindi recuperiamo. So I'm saying that if my initial condition is anywhere inside this circle of radius delta, clearly not larger than the circle of radius epsilon, the state evolution from any of these initial conditions will remain inside the circle of radius epsilon. Okay, it will not get outside epsilon. And I can choose this epsilon as small as I want. Or I can say that for any delta greater than 0, if I start inside my circle of radius delta, then the free evolution from this initial condition will not get outside the circle of radius epsilon. So this is the definition of stability. And this is the definition of stability of the specific equilibrium point, because this may happen for one equilibrium point and may not happen for a different equilibrium point in nonlinear systems. For linear systems, the situation was much, much cleaner. And that's why for linear systems, we were saying that the system is asymptotically stable. We were not saying the equilibrium point is asymptotically stable. Why? For linear systems, okay, to have, we know that the origin is always an equilibrium point. If it is the unique equilibrium point, okay, I will say that the origin is, for example, asymptotically stable. If I have more than, if e equals 0 is not the unique equilibrium point, then I cannot have asymptotic stability, because if I start from another equilibrium point, I will never get, for example, to the origin. Okay? So not only there's a nice property that the property in linear system of any of these equilibrium points implies and is implied by the property in terms of stability of the same property of all other points, which means if the origin is stable, or any other point, equilibrium point will be stable, and vice versa. If one of the infinite equilibrium points is stable, the origin is stable. All this to say that for linear system, we just can talk about stability of the entire system. There's no need to differentiate between equilibrium points. Either it is a unique equilibrium point, either if they are infinite, stability property of any of them implies the stability property, the same stability property of all others. But this is true only for linear systems. Let's take an example. I have somewhere, oops. Example. Let's take an example that we partially already met when we were talking about the phase plane, I think. So let's take this simple pendulum, okay? We write inertia times theta double dot, the contribution of the gravity, and if we want, we can add some viscous damping depending only on the linearly on the angular velocity. So this is a second order differential equation. It's nonlinear due to the presence of sign. And so we can rewrite this as usual as a set of first order differential equations, which of course are still nonlinear. Okay. I didn't put here any input. So this is just in the form x dot equal f of x. We said equilibrium points are such that f of xe equals 0. The derivative is 0. We solve, and we find that there's, of course, the 0, 0 state, which is an equilibrium point, but there's another one, which is pi 0. Remember, this is a position, and this is a velocity in our choice of the state. So these two equilibrium points correspond to the pendulum being still and pointing downwards, and the pendulum being still, 0 angular velocity, and pointing upwards. You see, two equilibrium points, of course, modulo 2 pi, okay? And these two equilibrium points, if we have our intuition, or if we start from a different initial condition, okay, it will go back to this equilibrium point. If I start from a different initial condition close to my other equilibrium point, it will diverge. So this equilibrium point will be, if we have damping, asymptotically stable. This will be unstable. And here, asymptotically stable means that not only I have the previous stability property, but I have that the trajectory goes back to xe. Okay, so, okay. So we have this example, and we already saw this phase plane. This is the case in which we have no damping. If we have no damping, the upward configuration is still unstable. The downward configuration is not asymptotically stable because the state evolution does not go back to xe. It will continue oscillating. Is it stable? Well, we could here, I'm not sure if I did it. We could here find through the definition, said, okay, I choose an epsilon. If I start somewhere here, all the state evolution will remain in the circle of radius epsilon, and this is what is shown here. Okay, so I invite you to go through this example and get this definition. Now, this new definition of equilibrium, of stability and the corresponding asymptotic stability, so we have xe is stable, and we have this solution. If given any, there exists delta, etc. Okay. xe is asymptotically stable if two conditions are verified. If it is stable, so the evolution is bounded, but not only the evolution is bounded, but the limit as t tends to infinity of xt minus x0 is 0. So xt, the state, goes back to the equilibrium point. But you could say, this example, I have two equilibrium points. if I start from that specific, if I look at this downward equilibrium point, if I start exactly from the other equilibrium point, for sure I will never converge to the downward one if I have no inputs, no perturbation. So for sure, any initial condition different from this second equilibrium point, if I have damping, will lead to convergence to the first equilibrium point. So it's not the convergence and stability property is not verified for all initial conditions, but just for a subset. In general, for nonlinear systems, these are local properties in the sense that they are true only for a subset of initial conditions, usually sufficiently close to the equilibrium point. Here, this is a very specific case. So the concept of the stability and asymptotic stability is local, okay? We can generalize this concept to global stability if we can prove that these property, asymptotic stability, for example, is true for all initial conditions. But we will not see the tools to do that. What we are going to see, let me just take directly these slides. No. Is this nice result, which is going to be extremely helpful, at least to have some, let's say, local information based on what we know on the stability of linear systems. So the idea is rather simple. The idea is, if I have a function, I could say, well, around this point, I can make an approximation through the tangent. So you see, I can approximate a nonlinear behavior, this curve, with a linear behavior. And this approximation, of course, will change if I want the approximation at a different point. And this is exactly what we're going to, come on. Sorry. Okay. Just one problem. Okay. So where we no. Sorry, just 1 second. I deleted the bookmark. So you see there's a lot you can skip in these slides. No. There we go. Page 46 in case I lose again. So the idea is exactly this linearization, local linearization. So let's start with an equilibrium point. So such that for the nonlinear system x dot equal fx, we have an equilibrium point xe such that if I start there and I have no input, there will be no evolution from that state. And then I do just a Taylor expansion, which you all know. So around this specific state. So I have the function evaluated at that point, then I have the derivative of f with respect to x evaluated again, and the first x minus xe, and then I have higher order terms. If we look carefully, this thing here is a matrix. And it's a matrix which is in general dependent from X. It's a Jacobian matrix. And we are going to evaluate this at XE. So it's going to be a constant matrix, independent from X. We change coordinates. We take the deviation with respect to the equilibrium point. Since XE is constant, C dot is equal to X dot, because derivative of XE dot is equal to 0. And we can rewrite the previous Taylor expansion in a more compact form, in which we have as new, let's say, variables, the deviation with respect to the equilibrium point. So we end up with the variation in time of the deviation is equal a constant matrix times the variation plus some extra higher order terms. And the linear approximation just consists in neglecting this. Since these are higher order terms, which means terms in X minus XE to the K with K greater equal than 2, if X is sufficiently close to XE, this will be really small. And so hopefully it will give no contribution. And the linear approximation consists in just focusing on this linear part of my approximation. So the derivative of the deviation from the equilibrium point is equal to a constant matrix, which now could be defined as my dynamic matrix, times the deviation. Okay, so we are now approximating locally. Locally means close to the equilibrium point, our nonlinear system with a linear one, in which this Jacobian, this matrix J, is evaluated at the equilibrium point. So we can now study the stability property of this linearized system. We can say that the linear system is stable, unstable, etc. And the main result is this indirect Lyapunov criteria, which states two important results. Be careful, it's not one-to-one linear to non-linear locally, and we're going to explore this. So if the linear system is asymptotically stable, which means that all the eigenvalues have a real part strictly less than 0, we can say that the equilibrium point XE is locally asymptotically stable. And that's very useful, because for a complicated nonlinear system, if we find an equilibrium point, we can study at least what happens if we do not deviate too much from that equilibrium point through the linear approximation. Then we have the opposite. If the linear system is unstable due to the presence, be careful, due to the presence of at least one eigenvalue with positive real part, then we can say that the nonlinear system has XE as an unstable equilibrium. You see, there's a whole world, a gray area, which we haven't, for which at least this method does not give us any information. And this area is what happens if we have eigenvalues of the linear approximation which are 0. we cannot say anything, okay? Even if they have a geometric multiplicity greater, different from the algebraic multiplicity, for which the linear system is unstable, we cannot say anything about the nonlinear system. And so this is the indirect. So let's take our pendulum example. I think in this M has been taken to 1. Let's see, somewhere. Okay. So this is, let's say, with some specific values of M, the previous pendulum example. We have 2 equilibrium points, the downward and the upward configurations. This is the Jacobian matrix. So this is computed as F has 2 components, F1 and F2, F of X. So this Jacobian is dF1 over dx1, dF1 over dx2, dF2 dx1, dF2 dx2, okay? This is how we compute the Jacobian matrix. We evaluate this matrix in the equilibrium point. This is a result for the linearized system in the upward. This is in the, downward and upward configuration. And if we compute the eigenvalues, we see that the linearized system is asymptotically stable here. And here we have an eigenvalue which is positive. So the downward equilibrium point is locally asymptotically stable for the nonlinear system, and is unstable for the upward is unstable for the nonlinear system. Okay. Now, there are situations why we cannot say anything about when we have eigenvalues equal to 0. Okay, the simplest case would be x dot equal minus x cubed. If we take this and we compute, so it's a scalar system. Jacobian is trivial, is minus 3x squared. If we compute this in xe equals 0, which is the unique equilibrium point, we have 0. So the linearized system is x dot equals 0 xe. We see that we have an eigenvalue 0. We cannot say anything. In reality, this system has the unique equilibrium point, which is asymptotically stable. It is even globally asymptotically stable. Okay, but the result we have just seen does not allow us to say anything about this. Okay. You can go back to the original slides. There are just another example with 0 damping. And there's another interesting case. If we look at this plot, okay, it's a phase plane of this system, which is a van der Pol oscillator. We see all these examples of trajectories. We see that they converge to somewhere. No, if you see the red dots, those are initial conditions, and you see they all converge to this, let's say, black line, which is defined as a limit cycle. So intuitively, we would say, well, this system is not asymptotically stable. The origin is an equilibrium point. So the origin is not asymptotically stable, but we have some kind of stability apparently. This is not true, okay? If you try, you choose, for example, this epsilon, well, any initial condition, you could restrain the delta as small as you want. Any initial condition different from xc will get out of this circle of radius epsilon. So the equilibrium point, our origin in this, for this system, is not stable in the sense that we defined, okay? So be careful, in nonlinear systems, things can get really pretty nasty. One last consideration on all this could be, clearly visualized in MATLAB. There's something here, okay. For example, I've built here in Simulink a simple, I want to see it all. A simple system. Okay. Zooming in MATLAB is always, I mean, in Simulink is always complicated. So you see, these are two integrators. So here on the left, you have, this is x1 dot, and here we have x2 dot. So this system reads as x1 dot is equal to, this function is a minus what comes in to the cube. So what comes in here is the output of this integrator. So it's x1. Okay, so here we have minus x1 cube. So x1 dot is equal minus x1 cube, and then we have an input plus u. Let's see x2 dot. x2 dot, this is x2. x2 is multiplied by minus 2. So we have x2 dot equal minus 2x2 plus 3x1. Okay, so the system equations are nonlinear. We have a two-dimensional system, and here we can look at the plot. In this example, I have put an input, a temporary input. Let me first take it out. You could study, you could not study this example with the result we saw, because it has 0 eigenvalue in the linear approximation. Okay, so the system starts from this initial condition and then goes to, asymptotically, it will tend to the origin here. I've stopped at 20 seconds. If I increase, it will go to the origin. So why did I'm also considering an input. You see this input, I mean, if we go inside, this starts at 1, goes constant value to 1. The second starts just a little bit later on and has a value minus 1. So the sum of these two signals is a square signal that starts in 1 and goes back to 0 in 1.3. So it's an input that is acting only on a small interval. If you think about the action of an input which is non-zero only during an interval, it will take my state, move it, and then the input stops. From that time on, it will just start from that initial condition and we'll have just a zero input response. And this is what now we should see in this simulation here. The no input is applied until time equal 1. At 1, my input is starting to act. It moves my state like this. At 1.3, the input goes back to 0. So we have a 0 input evolution. And again, the state is tending asymptotically to 0 in the X, Y plane. Okay, I will try to make these examples a little bit more clean and put it on the course Google group. I think it's about time for me to stop. And questions? If you have questions, prepare the questions for tomorrow because I think it's 5 minutes past 1, okay?
Professore, io ho solo una curiosità, ma sarebbe possibile organizzarsi per il ricevimento eventualmente online o bisogna necessariamente venire a Roma?